Hello everyone, my name is Shubhanshu. Today I'm going to look at a maths problem from the International Maths Olympiad 2021, and this is problem number 2. It's stated below. For people who don't know the International Maths Olympiad, it's basically like the Olympics for mathematics. I think like the age limit for this is like school students from all over the world. They participate here. Uh, all the problems from the Maths Olympiad can across the years can be found on the IMO website. This year's IMO actually concluded, I think, on July 28th. So we're going to look at one of the problems. Again, if you want to look at the actual tally for this year, um, this is the tally. So basically, rank 1 was achieved by China, followed by Russia, Korea, and then the US. And if you notice, like there are a total of 6 problems: P1, P2, P3, P4, P5, P6. Of course, each team has multiple contestants. So here you can see the team size. So each team actually has 6 contestants. So the maximum each consists, like the maximum team can score is basically all the contestants are able to solve the problem. And here you see like the maximum score is 42. So like as I'll show you in a minute, the each problem actually has the maximum score of 7. So like the team on its own can score a maximum of 42 points for each problem. And let's look at what the individual scores. So for example, like the total the highest individual score is like 42 by Yinxun Wang from China, and like I think this individual was able to score like 7 on all the problems. So pretty good solution. I Since I'm interested in problem number 6, problem number 2, so a lot of people were able to solve this problem quite successfully. But again, like if you go back to the team ranking, uh, no team was actually able to solve this, like score the maximum points on this problem. So I was a bit surprised by that. Again, like I only looked at these scores after I was able to give this problem a shot from my own side. So I'm mostly going to walk through my solution, but it was quite surprising to me that yeah, like yeah, like none of the team score full marks on this problem, which again, like made me also doubt my solution. So again, like my solution may have some errors. Feel free to point them out in the comment section. uh, but overall, I think like yeah, this is a pretty good problem, very easy to approach. And I think like yeah, like as I saw the individual scores, like some individuals were able to solve it. So that gave me a breather. So let's look at the problem now. Just to give you, like the IMO actually happens over 2 days. So Monday 19th of July and then Tuesday 20th of July. Each day the students get 3 problems to solve, and each problem actually is worth 7 points, and they get like around 4 hours, 4 hour 30 minutes of time precisely on each day. So a total of 6 problems. Every individual can score a maximum of 42 points, which counts towards them as well as towards their team. So now I'm going to focus on this problem. I haven't looked at all the other problems. This is the problem I'm most interested in. Again, like the reason it caught my eye was because inequality used to be one of my favorite subjects during my school time, and I've tried a few inequality problems from IMO and other Maths Olympiad, like a local level, which I found like quite interesting. So yeah, this problem was like uh, appeared a bit related to me from that side. So I thought like, okay, like why not give it a shot? Haven't tried a Maths Olympiad problem in a long time. So again, I might be wrong, but I think like based on the solution I've prepared, I feel fairly confident that it's like the right solution. Um, so let's read through the problems. The problem simply states that we have to show that this inequality, a double summation I1 to n, j1 to n, square root of xi minus xj is less than or equal to, again, double summation I1 to n, j1 to n, square root of the absolute value of xi plus xj. And we have to show that this inequality holds for all real numbers x1 to xn. The way I look at it is like basically what it's saying is that, like, a sum of all, if you give it like n numbers x1 to xn, the sum of all possible absolute square root of absolute differences is always less than or equal to the sum of all possible absolute square root of absolute totals of those numbers, or pairwise totals. Okay, so pairwise differences, pairwise totals, and that's the key idea. That's how I look at it. So I think like that should provide like some intuition to me, to us to to solve this problem. So let's walk through the solution I have. So first of all, again, because there's a double summation on both sides, I wanted to highlight what the differentiating items are on both sides. So on the left hand side we have the difference, on the right hand side we have the sum. Everything else remains same. So I tried the simplest thing. I arranged everything on one side and I got 0 on the other side. So basically I brought the right hand side on the left, and effectively we get this equation, which is this item comes on the left hand side, and we have this difference minus the sum is less than or equal to 0. So of course we can flip the negative sign, and we have the sum of all possible square root of absolute pairwise sums minus the sum of all possible square root of absolute pairwise differences is always greater than or equal to 0. So that's what the problem comes down to, and this is what I consider as the starting point of the problem for me. So effectively, if we prove this is true, then we also prove this is true. So let's see how we can proceed. So first of all, we have, as I showed you, we have this equation. So I denote the left hand side with this notation fx. So I call the left hand side is equal to fx, where x is basically this set of x1, x2, xn. So there's a function which takes as input the set of numbers, and this is what it computes. Now let's see what this fx appears to be. So first very obvious thing which came to me was that we can actually because it's summation on both of the items and it's the same index exactly, so we can actually move the summations outside and consolidate the terms together. So we can simplify it as summation, double summation I1 to n, j1 to n, square root of the absolute xi plus xj minus square root of xi minus xj, and that's the item we get. Of course, now our goal is if fx is greater than or equal to 0, we have to show that fx is greater than or equal to 0 for all possible x where x are these numbers. Again, I've used a slightly simpler notation, which is that x belongs to a vector of dimension n, and for all possible vectors, this is what we get as the function. So now let's consider the term again, moving from this part, let's just focus on the internal term of the summation, which is this term, the square root terms, and we are going to call these Fij, and so basically that's how I have written Fij is equal to the square root of the sums and the square root of the absolute differences. Okay, and Using this substitution, we now convert the original equation into like fx is equal to again double summation f of ij. And we can note one important thing, that Fij is actually is equal to Fji. This can be proven here, like so Fji is going to be because sum is commutative, so like order doesn't matter when you take a sum. So I plus xj remains same. This one xj minus xi. So in the earlier part we had xi minus xj, but again this is absolute value, so I can just like flip. Take the minus sign out, xi minus xj, and we already know for about absolute values, the absolute value of minus x is equal to the absolute value of x. So we can just use this substitution. So fji is equal to fij, and this is going to be very useful later. So once we know that this is the decomposition, we can actually like decompose this equation as follows. So we have again there's a mistake here, so let me just fix it. So we have fii, and then I is equal to 1 to n, j is equal to 1 to n, fij, and I'm going to talk about. So what I have done is basically I have decomposed from j, which is greater than I, and then here like for I do the reverse. So I because the summation I can do them in any order, so I go from j1 to n, I greater than j, and then I write it as fij. And this can again like using this fij is equal to fgi, we get this simplified form. So these two terms are actually like on the whole they are just like twice the original term, so fij, and I can write it in this form. I'm going to talk a bit about like how easy it is to see this decomposition in a minute. So just hold on for a second. Again, like this notation might be slightly complex for here. And the other thing which I also note is like we have this summation which is I is equal to 1 to n. So fii, this we can like easily compute. So fii we get like xi plus xi and xi minus xi. So this part goes to 0, this part goes to under root of 2 mod of xi, again which is equal to under root of 2 under root of mod of xi. So we know that this part is always greater than or equal to 0. It's positive because both these items are always positive. So effectively what we have done is that like we have decomposed the solution into these two items. We have fx is equal to this first term coming from ii, and then this 2 into this term which is this total minus the difference term. So now I wanted to bring back the intuition of how I was able to do the decomposition. So let's consider a different representation of the same problem. We have numbers from 1 to n, and now we can actually think of a matrix which actually has the right values for each of its ij elements. So if we have numbers xi and I numbers indexed by I and j, so we have like so for example this cell is going to be x0. So again I've used the 0 notation here, but like you can just add 1 here. So 0 based indexing I've used, but what you can use like this is x0 plus x0, and then this is going to be x1. So I'm going like this is the column indexing, so I'm going by column indexing, fine. So this is going to be x1 plus x0 and so on. So what we have is the first term, which is the square root of the absolute value of the totals, pairwise totals, and then similarly we have another term which is like the square root of the absolute value of the differences. And one important thing to note is that like as I showed you earlier, like this matrix is actually symmetric. So the total also actually comes out to be symmetric. So one very important thing to note here is this is always going to be 0 because all the items like it's if you have xi minus xi. So when I actually create a matrix which is like of the total, so I've basically just created this matrix with a random set of numbers, and you see that basically this fx is the total value. So fx is what we are after, so we have to prove that fx is always greater than or equal to 0, and this is the value I get, this is the matrix, and what fx actually comes out to be is the sum of all the entries in this matrix. So one thing to notice here is that this matrix is symmetric as well, which I've already shown before, and this actually allows for the decomposition. So we can actually, because this matrix is symmetric, we can decompose it into this sum of diagonal elements, which was the fii elements, and then there's the top triangle from the matrix and the bottom triangle. And because we know it's symmetric, the top triangle and the bottom triangle are going to be equal. So that's why like I can do this 2 into fij for I where j is greater than I. So like that's the substitution I did, and that's why this decomposition is better. I'm also going to use another simplification for this problem, because again we can always assume without any loss of generality that the xi's which we have are like somehow sorted. So there exists some ordering of xi's which is like x1 to x1 is less than x2 dot 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 x less than xn. Why it's possible? It's possible because of the nature of this problem, and as I showed you, what we are after is the sum of all the entries in this matrix. So the sum is going to remain the same no matter how we permute the rows and columns of the matrix. So all I've done is just sorted the rows and columns of the matrix, and I have created a more nicer looking matrix where the smallest value is first, the largest value is in the end. So basically what I've done is like I've sorted the values and then I've recomputed these matrices, and you see again like the sum should remain same, 57.53. It's exactly the same sum as before. It's just that like it's nicer to work with, and we can now it makes the proof slightly easier. Again, like I assume that it should be possible to do the proof without this assumption, but again like this assumption does not break anything from the problem, so it's a valid assumption to make. So now once we have all this intuition of how to break down this sum, how to decompose this sum, we go back to the original form. So we have fx is equal to these two terms. I've already showed you this was the diagonal term. This is twice the upper triangle, so because the upper triangle and the lower triangle are the same, so it's basically twice the upper triangle. And now let's just focus on this term, because I've already shown that this term is always positive. So, and in the end we really are hoping to just get like this whole thing is always positive. So we've already shown this is always positive, so all we care about is this, what property can we know about this item. So first we know that okay, this term actually has 2 into fij, as I've already shown you. And now because we made this assumption that xi is less than or equal to xj if I less than j, so like we can actually like start solving the problem. So let's go back and look at fij. It's this difference of two square roots, and what we can do is like take this mod of xi common. So what I've done is like divided the whole equation by mod of xi, and this gives me basically these two terms, and mod of xi I know like it's positive quantity, so the square root is also going to be positive, so we can just like take this out. So and it really should be yeah, it should be under braces. So yeah, that's my fault there. So now we have these two quantities, xj divided by xi, and then here 1 minus xj divided by xi. Of course this term is exactly the same in the two equations, so we can just substitute it by something called rij, which is equal to xj divided by xi. Now we know that xj is greater than or equal to xi based on the earlier assumption. So that means xj divided by xi is always going to be greater than or equal to 1. And this means that our ij is always going to be greater than or equal to 1. And we can use this and substitute it back to the equation. So we get this a nice equation in terms of our ij, and because we know this item is positive, so we don't have to worry about it right now. So let's go back and try to simplify it even further. So one very common technique which is often used to simplify when you have two square roots and you have these square roots which are of the form a minus b, so square root of a minus square root of b, is we can actually multiply and divide by this quantity which is square root of a plus square root of b. And what this gives is basically we can use the formula which is a minus b. So if you have x minus y into x plus y, it's equal to x squared minus y squared. So we can actually just apply here and we get the square root goes away, so we get a minus b, and then we have this divided by square root of a plus square root of b. And again really this quantity is always going to be positive because we are taking the positive square root, so nothing changes here in terms of the sign. So what we do get here is the simplification. We simplify and get these mods on top. So 1 plus rij absolute value minus 1 minus rij absolute value, and then we divide it by this additional term, which again we know it's positive, so we don't have to worry about it right now. So really the term of interest is the numerator. So let's see what we can do with it. So we know that rij is greater than or equal to 1. So we can actually know that 1 plus rij is always greater than or equal to 2. So that means this 1 plus rij quantity is always positive and it's actually always greater than or equal to 2. That means since it's always positive, we can actually just replace it with 1 plus rij equal to 1 plus rij. So we can just remove the absolute value and we can substitute it by 1 plus rij. So that simplifies things a little bit. Similarly, we can do it for 1 minus rij. So we can know that okay, minus rij is less than or equal to minus 1. So 1 minus rij is less than or equal to 0. That means this quantity is always negative. So now we can use this absolute value, that absolute value of something negative is equal to the minus of that value. So we can actually get the absolute value of 1 minus rij is equal to rij minus 1. And now we have these two equations. So we have simplified the top part, the blue part and the red part. So we go back and substitute it into our equation and we see how we go ahead. Okay, so we go ahead and now we are in the situation where we have these two items. So now use the substitution and we get the simplification 1 plus rij minus 1. So it gives us square root of xi and this whole term. So effectively rij and rij cancels and we are left with this should have been actually plus 1. So really so that's what the term becomes, and these two items cancel and then get 2. So effectively you have all these items are positive, so fij is greater than or equal to 0. So that becomes our actual fij value. So we have shown that fij is always positive because this term is positive, this term is positive, this term is positive, and again under the assumption that if the items are ordered correctly. So and we can make that assumption because we are really concerned about the total in the end. So now we go back and substitute this Fij into the final Fx, because remember, we made the assumption, but once we fit that assumption here, we get all these sorting guarantees. So once I substitute it here, I get back two terms, both of which are positive. So all the Fij's are positive. This term is already positive, so we basically get, like, this is greater than 0, and hence we can, like, show that the sum of two positive numbers is also positive. So if we have shown that Fx is greater than or equal to 0, so that's the proof. Just to recap, like, what are some of the core concepts I used. One was I represented this problem using a symmetric matrix, which we were able to use to decompose the problem into some parts which were which we could double basically, and also like the diagonal part. The second was, like, once we have that symmetric matrix representation, I was able to simplify it using this ordering, because all we care about is the total of that matrix. So the ordering of the elements should not matter, and I was used it to make the problem simpler. And then finally I was able to use another simplification of the square root, the difference of square roots, as a difference of the original numbers divided by some positive numbers. So this was also helpful. And lastly, I use the idea of how the absolute value can be resolved if we know that the internal value is all either positive or negative. So we were able to resolve it correctly, and that helped us complete the proof. So that's the proof. Again, there might be a few mistakes, but I'm personally quite confident of the solution. So yeah, feel free to point out any issues or with this proof. And also, like, I would be interested to know, like, what are some other variants which you have tried in trying to prove this concept. So yeah, that's it from my side. Thank you. I will be posting more videos soon, so thank you.